silence. Not the silence of an empty room, nor the stillness of a paused breath, but a silence so vast, it stretches between the stars. In the endless gulf of the cosmos, this silence is deeper than any human ear has ever known. A quiet so complete, it swallows even the faintest echo. It is here, in this boundless dark, that the universe hides its most unsettling secret. At the heart of collapsed stars, where gravity has triumphed over every opposing force, lies the singularity. A place where the known laws of physics collapse, where space and time themselves are pulled past the breaking point. Density climbs to infinity, volume shrinks to nothing, and the equations that once guided our understanding dissolve into meaninglessness. At the singularity, there are no maps, no rules, no answers. But perhaps the most haunting aspect is not what is destroyed, but what is forgotten. For in these abysses, even information, the universe's memory of what once was, may be erased. A star's fire, a planet's story, the trace of every particle and every light wave that crossed its skies, all reduced to silence without record. It is as if a cosmic eraser moves across the page of reality, stripping away not just matter, but the memory of its existence, a black ocean without echoes, where no history lingers, no voice returns. This is not merely the death of matter, it is the annihilation of meaning itself, and within this silence, deeper than the void between galaxies, lies the singularity that consumes all memory. In the early years of the 20th century, the universe itself seemed simple, almost eternal. Stars burned with steady light. Space stretched outward as an infinite backdrop, silent and unchanging. Physics too appeared complete, ruled by Newton's comforting laws of motion and gravity. Yet in 1915, Albert Einstein shattered this quiet symmetry with his theory of general relativity. He described gravity not as an invisible force pulling masses together, but as the bending of space and the warping of time itself. In his equations, mass and energy were no longer passive bodies drifting through a cosmic void. They were architects of space-time, sculptors of the very fabric of reality. General relativity was elegant, beautiful, and dangerously precise. It suggested that under certain conditions, gravity could fold space to an extreme collapsing geometry itself. Few at the time imagined that Einstein's new vision might lead to something terrifying. Places where space and time did not simply bend, but broke. The first to see this possibility was a German physicist, Karl Schwarzschild, writing from the mud and fire of the First World War in 1916. From the chaos of the battlefield, he solved Einstein's equations in exact form, revealing that if enough mass were crushed into a small enough region, space-time would collapse inward. At the center, the equations no longer made sense. The numbers spiraled toward infinity, pointing to a singularity, a boundary where the known universe ended and where no memory of physical law remained. Even Einstein himself resisted this conclusion. Singularities were unsettling, almost absurd. They implied infinities, breakdowns of order, regions of reality that lay outside mathematics itself. Most physicists dismissed Schwarzschild's solution as a curious artifact, a trick of calculation that could never exist in nature. Stars, they believed, would always find balance. Their pressure, their radiation, their fusion fires preventing collapse into the abyss. But the mathematics refused to disappear. In 1939, two young physicists, Robert Oppenheimer and Hartland Snyder, dared to take the equations seriously. They studied the fate of stars many times heavier than the sun, stars that could no longer hold themselves up when their nuclear fuel was exhausted. Their paper revealed a grim truth. Massive stars were doomed. When their internal fires faded, nothing could resist gravity's pull. They would collapse endlessly inward, faster and faster, until they crossed a point of no return. Beyond that horizon, not even light could escape. The star would vanish, leaving behind only a singularity wrapped in silence. Still, this conclusion was so radical that it was met with unease. Oppenheimer himself, years later, would turn his attention to nuclear weapons, leaving the cosmic problem unresolved. For decades, the singularity remained a shadowy prediction, a ghost lurking in mathematics, but unseen in the heavens. Then, in the 1960s, the silence broke. Astronomers, with new radio telescopes and X-ray detectors, began to glimpse strange and powerful objects in the sky. They found quasars, brilliant beacons blazing from the hearts of distant galaxies, outshining entire star systems, yet confined to regions smaller than our solar system. The only force capable of such power was gravity itself, unleashed in its most violent form. Soon after, X-ray telescopes revealed another enigma, a source in the constellation of Cygnus, flickering with unseen energy. Known as Cygnus X1, it emitted radiation, as if matter were being torn apart and devoured by something invisible. Careful measurement showed that it was paired with a massive star, and yet the companion was unseen, dark, and impossibly dense. The evidence pointed to one conclusion. Here was the corpse of a collapsed star, an object that fit Einstein's fearful equations. A black hole. For the first time, the singularity stepped out of theory and into the sky. What began as strange mathematics in the trenches of war had become an astronomical reality. The universe was not safe from collapse. Its stars, its galaxies, even its very fabric, could harbor places where time stopped, memory ended, and the laws of nature themselves dissolved. The discovery phase was over. Singularities were no longer hidden behind the veil of abstraction. They were real, and they had been watching us from the depths of space. When the mathematics of singularities first emerged from Einstein's equations, they seemed like distant abstractions, the ghosts of numbers rather than the bones of reality. But as observations in the 20th century piled up, quasars blazing across the cosmos, Cygnus X1 whispering of a devouring void, those abstractions solidified into a terrifying possibility. If singularities were real, then the universe contained places where physics itself unraveled. A singularity, in its simplest description, is a point of infinite density and zero volume. Every particle, every atom, every photon that crosses the event horizon is drawn inward, crushed beyond measure into a place where the laws that once governed them vanish. In such a realm, Einstein's general relativity, the very framework that predicted their existence, ceases to function. The smooth geometry of space-time collapses into chaos, and the equations fall silent. What remains is a question mark carved into the heart of the universe. For physics, this was not merely unsettling. It was catastrophic. Science thrives on predictability, on rules that describe the dance of particles and planets alike. But singularities offer no rules, only infinities. They are the places where knowledge ends. By the mid-20th century, the shock deepened as another branch of science entered the stage, quantum mechanics. Born in the 1920s, quantum theory revealed a universe ruled by probabilities, uncertainty, and the discrete behavior of particles. It thrived in the subatomic world, while relativity ruled the vastness of space and gravity. Yet at the singularity, these two great theories collided. Relativity predicted collapse to infinite density, while quantum mechanics refused to accept such infinities. Instead of harmony, the two pillars of physics fell into contradiction, and no theory could reconcile them. This fracture in science became most apparent in the 1970s when Stephen Hawking applied quantum reasoning to black holes. He discovered that event horizons, long thought to be perfect one-way barriers, could in fact leak. Through a process of quantum fluctuation, pairs of virtual particles could appear near the horizon, with one particle escaping while the other was consumed. The result was Hawking radiation, a faint emission of energy that slowly drained a black hole of its mass. Over vast spans of time, this process implied black holes could evaporate entirely, leaving behind nothing. But what of the information? This question struck at the deepest roots of physics. Every particle, every wave carries information. The details of its state, its position, its spin, its history. In quantum theory, this information is sacred, eternal. It cannot be destroyed, only transformed. But if a black hole evaporates completely, what becomes of the information locked inside? Does it vanish with the singularity erased from the cosmic record? Or does it somehow escape in the slow hiss of Hawking radiation? The paradox ignited one of the fiercest debates in modern physics. To allow information to vanish was to break the foundations of quantum mechanics. To preserve it seemed to defy relativity. In this clash, science confronted a possibility more disturbing than infinity: the erasure of memory itself. The universe, it seemed, was not only capable of destroying matter and energy, but also of annihilating history. If singularities erase information, then the record of everything that falls into them, stars, planets, perhaps civilizations, is lost forever. The cosmos becomes a place where the story of existence can be unwritten, where memory itself can be consumed. For many scientists, this revelation was almost unbearable. Physics is built on the assumption that reality is lawful, that no detail is ever truly erased, only hidden. But singularities threatened to reveal a universe indifferent to its own past. It was not merely a problem of calculation, it was a problem of meaning. Some argued that the information might be hidden on the event horizon itself, encoded in subtle patterns of space-time. Others speculated that the information might leak out slowly in the radiation, disguised in forms too complex to yet understand. But in the 1970s and 1980s, no consensus emerged. Instead, physics stood divided, staring into the abyss of the singularity and finding not clarity, but silence. The shock extended beyond equations and laboratories. Philosophers and scientists alike were forced to confront a deeper question. If the universe allows memory to be erased, what then of permanence? If black holes can consume not only stars, but also the very record of their existence, what does it mean to exist at all? The singularity became more than a scientific problem. It became a mirror, reflecting humanity's fear of forgetting, of dissolution, of becoming untraceable. In the darkness of these objects, in the silence of their horizons, lies a truth that physics was unprepared to face. Singularities are not only the boundaries of knowledge, they are the graves of memory, the erasers of history, the places where even the universe forgets itself. For a science built on the preservation of order, this realization was a rupture. For a species that clings to its stories, it was a wound. And yet, in this shock, a new determination was born. The need to understand, to seek theories that might rescue information from oblivion, to find out whether the universe truly forgets, or whether its memory is only hidden in form still, beyond human grasp. As the 20th century advanced, science turned its gaze toward the heavens with instruments of growing precision. The human eye, long limited by the shimmer of starlight, was replaced by machines that could see in wavelengths invisible to flesh and bone. Telescopes that once charted constellations now reached for the unseen. In this new era, black holes emerged not only as whispers of mathematics, but as celestial objects whose shadows could be traced by their effects on the world around them. The launch of the Chandra X-ray Observatory in 1999 opened one of the deepest windows into this mystery. X-rays, born in the violence of matter, accelerated and torn apart, poured from the edges of black holes. Chandra captured their patterns, painting images of disks of gas spiraling toward event horizons, heating to millions of degrees before vanishing into silence. Where stars once existed, there were scars of radiation, marks of an unseen predator. Each signal testified to the presence of objects so compact that no star, no neutron core could explain them. Only black holes fit the evidence. Yet even as Chandra revealed their edges, the interiors remained hidden. the event horizon, the boundary beyond which nothing returns, cloaked the singularity. Science could only study its outline, the shadow cast on surrounding space. Gravitational lensing, predicted by Einstein and confirmed decades later, offered another tool. Light itself bent around these invisible giants, distorted into arcs and halos, as if the cosmos were made of glass, warped by an unseen hand. These curved pathways revealed the presence of immense gravitational wells, places where space-time was twisted almost to breaking. The greatest laboratory for such studies lies at the heart of the Milky Way. There, 26,000 light-years away, stars orbit an invisible center with velocities so extreme that nothing ordinary could contain them. Year after year, astronomers measured their paths, watching them whirl around a point of darkness. This point, Sagittarius, A Ray, holds the mass of millions of suns within a region smaller than the solar system. Nothing but a supermassive black hole can explain such gravity. In their orbits, in their frantic speed, lies the evidence of an event horizon enclosing a singularity that swallows all memory of what falls within. The Event Horizon Telescope, a planet-sized array of synchronized observatories, pushed even closer to the edge. In 2019, it delivered the first image of a black hole, a glowing ring of fire surrounding a shadow. This was not direct sight of the singularity, but the silhouette of its horizon, the boundary between presence and absence. The picture was at once profound and unsettling. It showed the universe in the act of forgetting, matter burning with its last light before falling into silence. Theoretical work deepened the paradox. Stephen Hawking's radiation remained a haunting presence, a whisper that black holes are, not eternal but slowly fade. If this evaporation is true, then horizons are not merely prisons, but places of decay. Black holes are born, consume, and eventually vanish, leaving behind the question of what happens to the information that once defined them. At the center of this lies the no-hair theorem. Black holes, according to this principle, erase all distinctions. Whether a star was vast or small, ancient or young, composed of carbon, iron, or helium, once it collapses, its identity is stripped away. The black hole retains only three features: its mass, its spin, and its electric charge. Everything else is lost. All detail, all individuality is erased. In this reduction, complexity is annihilated. A civilization could fall into a black hole. Every structure, every record, every thought, and from the outside, it would leave no more trace than a simple increase in mass and perhaps a faint change in spin. This is the unsettling power of singularities. They do not only devour matter, they devour stories. They take the infinite variety of the cosmos, the layered interiors of stars, the chemistry of planets, the histories encoded in particles, and reduce them to sameness. Memory itself is flattened into simplicity, individuality into abstraction. In this deeper investigation, black holes cease to be distant curiosities. They become symbols of finality, reminders that the universe contains horizons beyond which not only matter but also meaning may vanish. The telescopes that capture their shadows, the detectors that trace their whispers, all point to the same reality. Singularities are not edges in theory, but edges in truth. For science, this knowledge is both victory and loss. Instruments have revealed what was once hidden, yet what they reveal is silence. The closer the gaze, the more profound the erasure. The cosmos itself holds within it the power to forget, to reduce all difference into unity, to erase the record of its own unfolding. And in that forgetting lies the deepest mystery of all. As black holes moved from speculation to evidence, their mystery only grew darker. At first, they were thought to be strange but simple outcomes of collapsing stars. Yet the closer science looked, the more they appeared not as answers but as contradictions. In their silence lay a riddle so profound that it threatened to unmake the very structure of physics. At the heart of this deepening crisis was the information paradox. Quantum mechanics, the foundation of the microscopic world, is unyielding in its demand that information can never be destroyed. Particles may scatter, decay, or transform, but the total information describing their quantum states must endure. Even the chaos of thermodynamics, the disorder of entropy, never truly erases detail, it only hides it. The universe, at its most fundamental level, remembers. Black holes seem to break this law. According to Einstein's relativity, once matter crossed the event horizon, it was lost forever. Its details, whether it was starlight or stone, hydrogen or human, collapsed into the same fate. And if Hawking's evaporation were true, then the black hole itself would eventually vanish, leaving behind no trace of what it had consumed. Information, it seemed, could be obliterated. For physics, this was not a small crack. It was a wound in the very foundation of knowledge, a contradiction between the two greatest theories of science. This paradox transformed black holes from exotic objects into existential threats to physics itself. They became arenas where the laws of relativity and quantum theory, each triumphant in its own domain, collapsed into conflict. The universe, which had always seemed governed by harmony, now appeared to hold contradictions at its core. Then, in 2015, another revelation struck. For the first time, humanity detected gravitational waves, ripples in space-time, born from the collision of two black holes more than 1 billion light-years away. Instruments at LIGO measured the stretching and squeezing of Earth itself as space-time rang like a cosmic bell. It was a triumph, a direct confirmation of Einstein's century-old prediction. Yet it was also a haunting reminder. The waves told of black holes merging, of horizons colliding, of masses so immense they shook the universe. But even in this moment of clarity, the singularity remained hidden. The ripples carried no memory of what lay within, no whisper of the information that had been consumed. The paradox endured. The escalation did not stop there. If singularities consume information inside black holes, could the entire universe face a similar fate? Cosmologists turned their gaze forward in time, imagining distant endings. One possibility is the Big Crunch, a reversal of cosmic expansion, where gravity halts the outward rush of galaxies and drags the universe inward. Stars, clusters, galaxies themselves could collapse into a final singularity, an ultimate horizon where all memory dissolves. In this vision, the universe ends not with fire or silence, but with forgetting. Others spoke of a more sudden doom, vacuum decay. Quantum field theory suggests that our universe may exist in a metastable state, like a ball resting in a shallow valley that is not the lowest point of the landscape. If a deeper vacuum exists, then one day, perhaps in the next instant, or perhaps in trillions of years, a bubble of true vacuum could form, expanding at the speed of light. Everything it touches would be rewritten. At its core would lie a new singularity, a new law of physics, erasing not only matter, but the very rules that define reality. Such scenarios transform singularities into more than astrophysical curiosities. They become cosmic horizons of meaninglessness, boundaries beyond which not only science but philosophy falters. If the universe can forget, if memory itself can be erased, then what is the value of knowledge? If permanence is impossible, if even the record of existence dissolves, what does it mean to exist at all? Here the mystery deepens beyond measurement, beyond experiment. Black holes cease to be objects alone. They become metaphors for the fragility of truth. They show that even the most rigorous theories can unravel when pressed to the edge. They reveal that within the very fabric of space-time lurks a silence vast enough to consume not only matter, not only energy, but memory itself. The escalation is not a crescendo of answers, but of questions. Physics stands at the edge of its own horizon, peering into a darkness where its laws dissolve. And beyond that horizon lies a silence the universe has not yet explained. A silence that may one day swallow all stories, leaving nothing but the shadow of forgetting. When the paradox of singularities reached its full weight, science was forced to stretch beyond the known. Black holes, once considered strange remnants of stars, had become riddles that threatened the very consistency of physical law. In response, physicists began to imagine new pathways, each theory an attempt to rescue memory from the abyss, each speculation a fragile bridge across the silence. The first light of possibility came from Stephen Hawking himself. His discovery of black hole evaporation, born from the restless dance of quantum fluctuations at the event horizon, suggested that information might not vanish so completely. In this view, as pairs of virtual particles emerged near the horizon, one particle falling in, the other escaping outward, the black hole would lose mass. The escaping radiation, though faint, might not be entirely random. Hidden within it, perhaps, encoded in subtle patterns, could be the information of what had fallen inside. If true, then no detail is truly lost. It only returns to the universe slowly, scattered like ashes on the cosmic wind. Yet decades of work have failed to show exactly how this encoding might function. The whisper remains uncertain, the promise incomplete. Another vision emerged from the holographic principle, first proposed by Gerard 't Hooft and expanded by Leonard Susskind. This principle suggested that all the information swallowed by a black hole is not destroyed, but preserved at its horizon. In this view, the event horizon acts like a cosmic film, a two-dimensional surface encoding the full three-dimensional story of everything within. A black hole is then not a grave, but a vault, its information flattened onto the edge of space-time. This principle grew beyond black holes, becoming a sweeping speculation that the entire universe itself might be holographic, with reality as we know it projected from deeper, hidden dimensions. Yet not all theories are gentle. The firewall hypothesis imagines that the horizon is not smooth, as relativity describes, but violent. In this model, as matter approaches the boundary, it encounters a wall of searing energy, destroying it completely before it can cross. This preserves quantum mechanics, for nothing truly enters, but it contradicts Einstein's vision of a seamless descent through space-time. A firewall solves one paradox only by igniting another. Other physicists turn to quantum entanglement, the strange linkage between particles separated by vast distances. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that entangled particles might be connected through microscopic wormholes, tiny bridges in space-time. If so, black holes themselves could be linked in hidden ways, with information escaping through threads of entanglement. In this picture, black holes are not solitary prisons, but participants in a vast quantum web, their horizons less absolute than once thought. Deeper still lie the attempts to unify relativity and quantum mechanics. Loop quantum gravity proposes that space-time itself is not continuous, but built from tiny quanta, indivisible loops woven together like threads in a cosmic fabric. In this view, singularities are illusions, avoided because space cannot collapse below its smallest unit. What appears as an infinity is instead a boundary of granularity, where information is preserved in the weave of space-time itself. String theory offers another vision. It imagines that all particles and forces are vibrations of tiny strings existing in higher dimensions beyond human sight. Within this framework, singularities may not exist as points of destruction, but as complex configurations where the strings of space-time rearrange. Memory might survive in hidden dimensions, safe from erasure, waiting beyond the veil of the horizon. But there are speculations more haunting still. Quantum field theory leaves open the possibility that the vacuum of space is unstable. If our universe is not in its lowest possible energy state, then one day a bubble of true vacuum could form. It would expand at the speed of light, rewriting the laws of physics as it spread. In that instant, all structures, all histories, all information would vanish into silence. Not even Hawking radiation, not even holographic surfaces could preserve memory, It would be a singularity of the entire cosmos, a final erasure written into the very instability of reality. Each theory is both salvation and despair. Some promise that information is preserved, encrypted in subtle codes or hidden in unseen dimensions. Others admit the possibility that memory may truly be lost, sacrificed at the boundaries of physics. All of them are born from the same desperation, to reconcile the paradox, to prevent the universe from forgetting itself. Yet, in their diversity, these speculations reveal something profound. The singularity has forced science to imagine beyond what is known, to stretch thought toward horizons not yet visible. It has become both an enemy and a muse, tearing at the fabric of physics while inspiring new visions of reality. Whether the answer lies in radiation, in holograms, in wormholes, in loops, or in strings, one truth is inescapable. The singularity is no longer only a place in space. It is a frontier of thought, a mirror reflecting the limits of human knowledge, and the silence against which all science must speak. The mystery of singularities has not remained confined to the abstract halls of mathematics. It has become a question pursued with instruments that stretch human ingenuity to its very limits. Around the globe and in orbit above Earth, machines of astonishing sensitivity now probe the universe, each one designed to bring the horizon closer, to test reality at the places where it begins to fracture. The most direct glimpse into the darkness came from the Event Horizon Telescope. This global array of radio observatories, linked together to form a virtual Earth-sized lens, captured the unseeable. In 2019, it unveiled the first image of a black hole, M87 Sao, a giant lurking at the heart of a distant galaxy. What appeared was not the singularity itself, but its shadow, cast by matter spiraling at near-light speeds around the event horizon. The dark core, encircled by a fiery halo, was a visual echo of predictions drawn decades earlier from Einstein's equations. In 2022, the telescope turned inward toward the center of the Milky Way, revealing Sagittarius A, the black hole anchoring our own galaxy. The images were blurred by the turbulent interstellar medium, yet they carried a revelation. The horizons of black holes were no longer untouchable abstractions. Humanity had begun to see the outlines of the unknowable. But light alone cannot carry the full story. To hear the cosmos, scientists turned to the ripples of space-time itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded the collision of two black holes, an event that had unfolded over 1 billion years earlier. The signal was unimaginably faint, a stretching and squeezing of space-time smaller than the width of a proton. Yet it rang through the detectors, confirming Einstein's century-old prediction. With that detection, the universe itself became an instrument, vibrating like a vast cosmic bell. Each merger revealed not only the existence of black holes, but their masses, their spins, their violent unions. LIGO, joined by its European counterpart Virgo, has since chronicled dozens of such events, opening a new window into the most extreme tests of relativity. Still, even these waves, born from titanic collisions, reveal nothing of the singularity itself. The center remains cloaked, as if space-time refuses to surrender its final secret. Meanwhile, beneath the Earth, another search unfolds. In the vast tunnels of CERN, protons are hurled at near-light speeds, colliding with energies that mimic conditions a fraction of a second after the Big Bang. The Large Hadron Collider was built not only to confirm the Higgs boson, but to probe deeper, searching for cracks in the Standard Model, hints of extra dimensions, or signals of quantum gravity. If black holes erase information, then the key to solving that paradox must lie at the crossroads of the very small and the very massive, the place where particle physics and relativity overlap. So far, no decisive answers have emerged. The soul, singularity waits untouched, but the search presses forward with every experiment, every collision. The horizon of exploration now extends into the future. Planned missions promise to push even closer to the edge of the mystery. The Laser Interferometer, Space Antenna, LISA, will orbit the Sun in a triangular formation, with detectors millions of kilometers apart, sensitive to the low-frequency murmurs of merging supermassive black holes. With LISA, space-time itself will be heard on scales never before possible, carrying whispers from the earliest galaxies. The James Webb Space Telescope, already peering into the depths of cosmic time, brings its infrared vision to the environments around black holes, tracing the growth of galaxies and the role of their central singularities. Every photon Webb collects is a fragment of history, part of the story of how darkness sculpts light. Together, these tools form a chorus of observation, each tuned to a different register of the cosmic song. Images of horizons, echoes of mergers, collisions of particles, the glow of distant galaxies, all converge upon the same question: what truly happens at the singularity? Does memory perish there, or does it escape encoded in ways not yet understood? This is not merely a question of black holes. It is the search for quantum gravity, the elusive theory that would unite the smooth fabric of relativity with the granular uncertainty of quantum mechanics. Without it, the paradox remains unresolved, and the universe itself remains inconsistent. With it, humanity might finally glimpse what lies beyond the veil, whether the cosmos forgets, or whether, in its deepest structure, nothing is ever lost. For now, the singularity endures as a silence at the heart of science. But every photon captured, every ripple recorded, every particle collision analyzed, brings the silence closer to breaking. The mystery deepens, but so does the resolve. The tools of human curiosity grow sharper, reaching further. And in that, relentless pursuit lies a quiet truth. Even if the singularity conceals the universe's memory, the search for it ensures that nothing is forgotten. Silence. In the beginning, it was only a pause between words, the stillness between the stars. But here, at the edge of the singularity, silence takes on a deeper meaning. It is not the absence of sound. It is the absence of memory, a void where not only light and matter are consumed, but history itself. If the singularity is real, then the universe may contain places where time collapses and records are erased. A star that once burned with brilliance, a world that may have harbored oceans and voices, even the faint trace of a single photon, all reduced to the same nameless state, indistinguishable from anything else that has fallen into the abyss. It is not merely destruction, it is forgetting. This possibility unsettles more than physics. It unsettles the very idea of existence. What is the meaning of being if what has been can vanish without record? Does life matter if its memory is erased by the fabric of reality itself? Or is meaning not in permanence, but in the fleeting act of presence, in the fact that for a moment, however brief, the universe knew itself through us? For humanity, black holes and singularities are more than distant astrophysical puzzles. They are mirrors reflecting back our own fragility. They remind us that permanence is an illusion and that memory, the archive of identity, of civilization, of cosmos, is not guaranteed. They whisper that even the universe itself may one day face erasure, drawn back into a final singularity where all that ever was dissolves into silence. Yet the mystery remains unresolved. Perhaps singularities do not destroy memory, but transform it. Perhaps the information is encoded in ways still hidden from human comprehension, woven into the holographic surface of horizons, or carried through entanglement to distant places. Perhaps silence is not the end, but only the threshold of a language not yet understood. And so the singularity stands, both terrifying and beautiful, the silence at the heart of creation, the reminder of our limits, and the challenge to go further. It waits in the darkness, not only as a riddle of physics, but as a question of meaning itself. Does the universe forget? Or is memory never truly lost, only waiting beyond horizons to be discovered in another form? The silence does not answer, it only deepens. In the end, the singularity is not only a boundary of physics, It is a boundary of meaning, a place where even memory trembles, where the universe itself seems to hesitate between remembrance and forgetting. Perhaps everything vanishes there, or perhaps everything is preserved in a form we cannot yet read. Until the day we know the silence remains, vast, unbroken, and eternal. And within that silence lies the greatest question of all. When the universe forgets, who will remember that we were here